There is a design locked inside a government archive that could have put 150 people on Mars and brought them home in roughly 10 days. The spacecraft was called Orion, and almost no one has heard of it. It was studied for 7 years by some of the same physicists who built the atomic bomb. It had serious government funding. It had a preferred trajectory to Mars already mapped, and then, quietly, it was cancelled. What's strange is how close it came to actually being built, and what it would have meant if it had. To understand what Orion was, you first have to understand the problem it was trying to solve. By the mid-1950s, rocket engineers had a fundamental issue. Chemical rockets, the kind that burn liquid hydrogen and liquid oxygen, are extraordinarily powerful, but they are deeply inefficient. Almost all of the mass you put on the launch pad is fuel. The actual payload is a tiny fraction of the total weight. When NASA eventually sent Apollo to the moon, only about 5% of the vehicle sitting on the launch pad was the part that actually went anywhere useful. That works fine for the moon. The moon is close, but Mars is not close. Mars, at its nearest approach to Earth, is still tens of millions of miles away. A chemical rocket heading to Mars would need to carry so much fuel that the equation starts to break down entirely. The more fuel you add, the heavier the rocket. The heavier the rocket, the more fuel you need to lift it. It becomes a problem that folds in on itself. Engineers knew this. It was not a mystery. And for a small group of physicists in the late 1950s, it pointed to an obvious conclusion. The answer was not more chemical fuel. The answer was something else entirely. The idea had actually been sitting in a classified document since 1946. A mathematician named Stanislaw Ulam, one of the key figures behind the hydrogen bomb, first proposed it in a paper that year. What if, instead of burning fuel inside a rocket engine, you detonated nuclear explosions behind the spacecraft? A series of them. Hundreds of them, spaced precisely, pushing the craft forward with each pulse. Ulam worked through some early calculations with a colleague named Frederick Rines in a classified Los Alamos document dated 1947. The numbers were promising enough that the idea didn't disappear. It sat, classified and quiet, for nearly a decade. Then, in August 1955, Ulam co-authored a formal classified paper. The paper proposed using nuclear fission bombs detonated at a considerable distance behind the vehicle as a propulsion system for spacecraft. The key word there is distance. The bombs would not be exploding inside the rocket. They would be exploding behind it, in open space, and the spacecraft would absorb the push. This is the paper that quietly started everything. 3 years later, in 1958, a physicist named Ted Taylor took that concept and turned it into a real program. Taylor worked at a company called General Atomics in San Diego. He had spent his career at Los Alamos designing nuclear weapons specifically, making them smaller and more efficient than anyone thought possible. Taylor had a particular kind of mind. He thought in concrete objects rather than equations. And what he saw, at Ulam's idea, was a spacecraft that could go anywhere. In July 1958, the Advanced Research Projects Agency, known today as DARPA, agreed to fund the project at an initial level of $1 million per year. The program received its name at that point. They called it Project Orion. Now, here is how it actually worked. The spacecraft would carry a large supply of what the designers called pulse units. These were small nuclear devices, essentially atomic bombs, stored in the interior of the ship. A mechanical system, not unlike the mechanism inside a vending machine, the Coca-Cola company was actually consulted on the design, would dispense these devices one at a time. Each pulse unit would be ejected through a hole in the bottom of the spacecraft. It would travel roughly 20 to 30 meters behind the ship before detonating. Beneath the spacecraft was a large, thick steel plate. The designers called it the pusher plate. When the bomb detonated, it produced a rapidly expanding wave of plasma and radiation. That wave would slam into the underside of the pusher plate, delivering a massive, nearly instantaneous push. The pusher plate was connected to the rest of the spacecraft through a set of enormous shock absorbers. Those absorbers would smooth out the impact, converting what would otherwise be a violent, bone-shattering jolt into a sustained, manageable acceleration. The crew, sitting above the shock absorbers, would feel something between 2 and 4 times normal gravity. Not comfortable, exactly, but survivable, and the process would repeat roughly once per second. Each explosion adds momentum. Each one pushes the craft a little faster. And because nuclear fuel contains so much more energy per unit of mass than chemical fuel, the difference is roughly 1,000,000 to 1. The spacecraft doesn't need to carry anywhere near as much propellant to go much farther. The key figure here is something engineers call specific impulse. It's a measure of how efficiently a propulsion system uses its fuel. A good chemical rocket achieves a specific impulse of around 450 seconds. Nuclear thermal rockets, the kind that heat hydrogen by running it through a reactor, can reach around 900 seconds. Orion's original interplanetary design was projected to achieve somewhere between 2,000 and 6,000 seconds. A later proposal, incorporating fusion rather than fission, projected values well above 75,000 seconds. Those are not small differences. They are differences that change what's physically possible. So let's talk about what those numbers actually meant in practical terms. The standard interplanetary Orion design, what the team called the base design, was a spacecraft massing around 4,000 tons. It was 40 meters in diameter, 60 meters tall. It would have carried roughly 800 pulse units to reach orbit from the ground. After that, it had payload capacity to Mars and back of around 800 tons. 800 tons of payload to Mars and back. The Saturn V, the most powerful rocket ever actually flown, could send approximately 2 tons to the lunar surface, not to Mars, to the Moon. Now here's what that disparity actually produced in terms of mission planning. NASA produced a Mars mission profile for the Orion design. The mission called for a crew of 8 astronauts. It projected a round trip of 125 days. The estimated development cost was $1.5 billion, roughly the same as the Apollo program, which sent 12 people to the Moon and no farther. The Orion mission would have sent 8 people to Mars and back. And those 125 days? That's the full round trip. Many modern proposals for Mars missions call for one-way travel times of at least 9 months, before even accounting for the return. The reason Orion could do this is energy. Not efficiency in the conventional sense, not squeezing every drop out of a limited supply, but raw, abundant, almost reckless energy. Nuclear explosions produce so much force that the spacecraft didn't have to follow the fuel-conserving, slow, curved paths that chemical rockets are forced to take. It could travel something close to a straight line, the fastest practical path between 2 planets. This is what made the design extraordinary, and also what made it controversial. There are a few details about the engineering that are worth sitting with. The pusher plate was the most important component of the entire spacecraft. It was the surface that would absorb repeatedly the force of nuclear explosions happening roughly 80 feet away. This sounds impossible, but there's a reason it isn't. When a nuclear bomb detonates, it expands outward at extraordinary speed, roughly 2.5 million miles per hour. The shock wave arrives at the pusher plate and delivers its energy so quickly that the plate is pushed away before the heat has time to cause serious damage. This is counterintuitive. We tend to think of heat as the main danger from an explosion, but at these timescales, microseconds, the shock wave acts first. The Orion team confirmed this with actual experiments. They suspended steel spheres coated with graphite near nuclear test explosions at Eniwetok Atoll. The spheres survived. A thin layer of the graphite surface had ablated been stripped away, but the steel underneath was intact. This told them something crucial. A plate didn't need to survive the full thermal energy of an explosion. It just needed to survive the brief initial shock. And if you sprayed the plate with a thin coating of oil or grease between each detonation, even the surface ablation dropped to nearly zero. So the engineering team knew the plate could work. The question became how to build it correctly. They determined that the plate should be thicker at the center and taper toward the edges. This was not obvious. Early tests with uniformly thick aluminum plates showed that the shock wave created uneven stresses, and the plates shattered. The tapered design corrected this. The team confirmed it through a series of model tests using chemical explosives at Point Loma in San Diego. The shock absorber system was another significant engineering challenge. The first proposal used large pneumatic bags, essentially inflatable rings between the plate and the spacecraft body. This design had a problem. If a pulse unit failed to detonate, the pusher plate would rebound upward and potentially tear the airbags apart. The team replaced them with a two-stage system of mechanical springs and gas pistons, carefully tuned to the frequency of the explosions. The final design could even tolerate a complete bomb failure and restart cleanly. The bombs themselves, the pulse units, were also a substantial design challenge. Each one needed to be small enough to be handled mechanically, durable enough to survive being ejected at speed, and precisely shaped to direct most of its explosive energy toward the pusher plate, rather than outward in all directions. The team developed a design using what they called a nuclear-shaped charge. The bomb's geometry focused its energy in a specific direction. The propellant, a flat plate of tungsten, would be vaporized by the explosion and transformed into a cigar-shaped wave of plasma aimed directly at the pusher plate. This focusing was what made the system efficient. A spherical explosion wastes most of its energy. A directed explosion uses it. Each pulse unit was designed to weigh just over 300 pounds and fit inside a canister no more than 6 inches in diameter, small enough to be moved by machinery derived from a soft drink vending machine. The plasma from each detonation, by the time it reached the pusher plate 25 meters away, would be at a temperature of around 14,000 degrees Celsius. It would reheat upon impact to around 67,000 degrees. At those temperatures, it emits ultraviolet light rather than visible light, and ultraviolet light is poorly transmitted through most plasmas, which helped keep the plate from absorbing excessive heat. Every one of these details was worked out by the project team between 1958 and 1964, not in theory, in experiments, in model flights, in plasma generators and nuclear fireball tests, and careful measurements taken from materials exposed to actual detonations. This is not speculation about what might work. This is engineering that was done. It's worth pausing here to talk about who actually built this. Ted Taylor led the project at General Atomics. He had been one of the most creative bomb designers at Los Alamos, the person who made nuclear weapons smaller and more efficient than anyone thought the physics would allow. Freeman Dyson, one of the most respected theoretical physicists of the 20th century, took a year away from the Institute for Advanced Study in Princeton to work on Orion at Taylor's request. Dyson said later that the 18 months he spent on the project in California were among the happiest of his life. The team also included Stanislaw Ulam, who had originated the concept. And supporting the project was Wernher von Braun, the same engineer who would later lead the Saturn V program. Von Braun was initially skeptical. He sat through one of Taylor's presentations with his eyes closed, and Taylor thought he was asleep. Then Taylor showed him film of the model tests, small Orion prototypes blasting themselves into the sky on chemical explosives, and von Braun sat bolt upright. He became a vocal advocate. The project attracted support from physicists including Niels Bohr, Hans Bethe, and Harold Urey. Carl Sagan later suggested that Project Orion would be an excellent use for the world's stockpiles of nuclear weapons. This was not a group of dreamers on the fringe. These were the people who had built the bomb, who had designed the Saturn V, who had established the foundations of modern nuclear physics, and they believed not as a fantasy, but as a technical assessment that Orion was workable. The team's internal motto captures what they thought they were doing. It was simple and direct. Mars by 1965, Saturn by 1970. One thing that gets lost in the technical discussion is the sheer scale of what was being proposed. The smallest Orion design that the team considered practical, what they called the orbital test vehicle, massed 880 tons. It was 25 meters in diameter and 36 meters tall. Its payload to low Earth orbit was 300 tons. The base interplanetary design was 4,000 tons, 40 meters in diameter, 60 meters tall. There was a larger version, 10,000 tons, 56 meters in diameter, 85 meters tall, payload to Mars, orbit and back, over 5,000 tons. And then, in the General Atomics Report of 1959, there was a design that went much further. A spacecraft they called the Super Orion. The Super Orion was 400 meters in diameter, 8 million tons. Freeman Dyson himself contemplated it and spent an afternoon calculating how heavy the city of Chicago was to see whether something of that scale was conceivable. It was. In principle, the designers described the Super Orion as a potential interstellar ark, a self-contained civilization that could leave the solar system entirely. The materials required to build it existed in 1958. This is the point at which the project stops feeling like engineering and starts feeling like something else, something closer to a question about what the human species might have chosen to become if events had unfolded differently. But here's the part that the project never fully solved. Launching from the ground meant nuclear explosions in the atmosphere. Every launch would produce radioactive fallout. Freeman Dyson estimated, using the calculations available at the time, that each Orion launch from Earth's surface would statistically cause somewhere between 1/10 and 1 fatal cancer from fallout. He was using what engineers call a no-threshold model, the same method used to estimate statistical deaths from other industrial activities. The number is not zero, but it is also, in context, small. Dyson's own estimate was that the most extensive launch program they envisioned would add no more than 1% to the atmospheric contamination then being produced by the nuclear weapons testing of the major powers. Ted Taylor believed that with the right bomb designs specifically, designs that maximized fusion yield and minimized fission fallout, the radioactive output could be reduced by a factor of 10 or potentially eliminated entirely. But that required a pure fusion explosive. And a pure fusion explosive, as of 1964, had not been successfully developed. So the ground launch problem was real. The team had proposed alternatives, launching from very remote locations, launching from the ocean, or using conventional rockets to carry the Orion vehicle to orbit first, where it would ignite its pulse propulsion system in space. The Saturn V upper stage was specifically proposed as a way to get Orion into orbit cleanly, with no nuclear detonations in the atmosphere at all. But this created a different problem. To get a 4,000-ton spacecraft into orbit on Saturn V rockets, you would need multiple launches and orbital assembly. The economics started to look complicated. And NASA, which had committed to chemical rockets for the near future, was not enthusiastic about building assembly infrastructure for a nuclear spacecraft. There were also concerns about electromagnetic pulses from the detonations, which could damage satellites and electronics, and about the Van Allen radiation belts, which could be temporarily filled with high-energy particles from low-orbit nuclear detonations. These were not necessarily fatal problems. They were engineering challenges. Some had proposed solutions. Others remained open, but they were real. The project was cancelled in 1964. The immediate cause was the Partial Test Ban Treaty of 1963, signed by the United States, the United Kingdom, and the Soviet Union on August 5th of that year. The treaty prohibited all nuclear detonations except those conducted underground. Orion, which depended on nuclear explosions in the atmosphere or in space, was now, in its practical form, illegal under international law. There had been an attempt to include an exception in the treaty, a carve-out that would permit nuclear detonations for peaceful spaceflight purposes. Soviet concerns about military applications kept the exception out of the final text. There were other reasons too. NASA had decided, as early as 1959, that the civilian space program would be non-nuclear in the near term. The agency was politically sensitive, and nuclear propulsion, however sound, the engineering carried a public perception problem that NASA's leadership was unwilling to take on. NASA was also filled with engineers who had spent their careers building chemical rockets and were, in some cases, openly opposed to nuclear propulsion. The Air Force, which had taken over funding for the project after DARPA withdrew support in 1959, was willing to continue only if a military use could be demonstrated. Some in the Air Force wanted to turn Orion into a weapons platform. The designers resisted this. The tensions were real, and they drained the project of its political coherence. By the time it ended, roughly $11 million had been spent over 7 years. In that time, the team had designed 3 full vehicle configurations, run hundreds of model tests using chemical explosives, built and tested a scale model spacecraft that flew successfully in November 1959, rising to a height of 56 meters on 6 chemical explosions and landing by parachute, undamaged, and produced a detailed Mars mission profile. The 1-meter model from that November 1959 test is now in the collection of the Smithsonian National Air and Space Museum. The wooden display model of the full Orion spacecraft, 26 inches tall, is at the Stephen F. Udvar-Hazy Center in Fairfax County, Virginia. Freeman Dyson later said that the cancellation of Orion was, in his view, the first time in modern history that a major expansion of human technology had been suppressed for political reasons. He came to revise that view somewhat in later decades. By the 1970s, he had become more concerned about the fallout problem and less certain that Orion was the right path forward. He wrote in retrospect that he would not wish to fly in a ship that deposits radioactive debris on the passengers of what he called Spaceship Earth. Ted Taylor, who had been the project's driving force, spent the rest of his life working on nuclear materials, safeguards trying to ensure that the same weapons he had spent years making smaller and more efficient could not be misappropriated or misused. He never stopped thinking about the stars. Orion did not simply disappear. The ideas it developed kept moving, even after the project closed. In 1968, Dyson published a paper in Physics Today called Interstellar Transport. In it, he extended the Orion concept to interstellar distances, replacing fission bombs with 1 megaton deuterium fusion explosions. His calculations showed that a momentum-limited Orion design, a ship 100 meters in diameter, massing 100,000 tons, could potentially reach 1% of the speed of light. And that, if accelerating at 1 standard gravity, it could reach that speed in roughly 10 days. 10 days of acceleration, to get to speeds that no human spacecraft has ever approached. The British Interplanetary Society built on these ideas between 1973 and 1974 in a project called Daedalus, a proposed robotic interstellar probe designed to reach Barnard's star at 12% of the speed of light, using fusion microexplosions rather than full nuclear devices. In 1989, the US Navy and NASA studied a similar concept in Project Longshot. From 1998 onward, researchers at Pennsylvania State University have been developing 2 further versions of the concept, using compact antimatter catalyzed nuclear pulse propulsion. None of these later projects have been built. Some require fusion technology that does not yet exist, but they are serious work, done by serious people, in the direct intellectual lineage of what Taylor and Dyson and Ulam started in San Diego in 1958. And there is one more detail that has remained partially classified for decades. In the final years of Orion's existence, under Air Force funding, the team began exploring modifications to the pulse unit design. A directed nuclear pulse unit, one that focused its plasma into an extremely tight, high-velocity beam rather than a broad push against the pusher plate, could theoretically serve as a weapon. The concept was given a name, the Kasaba howitzer. Declassified information confirms that the concept was real, and that development continued after Orion itself was cancelled. Most of the details remain classified. What we know is this. The nuclear-shaped charge that was designed to push Orion through the solar system was, in a different configuration, also a directed plasma weapon, capable of striking targets at distances usually associated with high-powered lasers. That is what can be said publicly. So what do we make of all this? Here is what we know so far. In 1958, a small group of physicists proposed a spacecraft that could carry 150 people to Mars and back in roughly 10 days, using technology that already existed. They spent 7 years developing the engineering. They built and flew a working-scale model. They produced a detailed mission profile. They had the support of some of the most accomplished scientists of the 20th century. And then a treaty was signed, and a political decision was made, and the project ended. Here is what the data suggests. The core engineering of Project Orion was sound. The pusher plate concept was validated by experiment. The shock absorber system was workable. The pulse unit design was specifically engineered. The fallout problem, while real, had proposed mitigations, and some researchers believed it could be reduced to near zero with better explosive designs. Some researchers argue that the political decision to cancel Orion was simply a reasonable response to the genuine danger of nuclear fallout and the legitimate concerns of the public. Others argue that it was, as Dyson put it, the suppression of a technology for political reasons, and that the decades of slow, expensive, chemically propelled space exploration that followed were the cost of that decision. What if the test ban had included an exemption for peaceful spaceflight? What if NASA had chosen to support nuclear propulsion in 1959 instead of turning away from it? What if the $11 million spent on Orion had been $15 billion? We don't know. These are counterfactuals. History doesn't run twice. What we do know is that the spacecraft was real. The physics was real. The engineering was real. A 1-meter model flew to 56 meters on chemical explosives in November 1959 and landed by parachute, intact. And somewhere in a government archive and in the collection of the Smithsonian, there is a wooden model of a ship that might have reached Mars before the Apollo program reached the Moon. The more you study Orion, the stranger the silence around it becomes. For now, all we can do is look at what was built, read what was written, and sit with the question that the project leaves behind, not just about propulsion, or physics, or engineering, but about what we choose to do with what we know. Every answer brings another question. And that, in the end, is how science moves forward.